Greetings. We're going to look at two properties of vector fields, the curl and the divergence. And roughly, they both come into play when you play with the gradient operator, like a vector differential operator, and these gradients. So the curl, roughly speaking, is it measures and indicates how much a vector field rotates. And actually the curl differs from point to point. So you would actually find what's the curl at this point in the vector field? What's the curl at that point in the vector field? So what is a curl? The curl is actually defined as this, the curl of a vector field is a vector field itself. So the curl of a vector field at a certain point gives you a vector. Okay, and when the vector field is defined in the way that, like, when we're saying that if f is p q r, right? So the first component is p, the next component is q, the next one's r. The curl is defined as the partial derivative of r with respect to y minus partial of q with respect to z times the I vector, right? And then the second component and the third component are given in this way. Now this is not so obvious, it's not so easy to memorize, but if you if you kind of create this differential operator, and the curl is really the cross product of the differential operator and the vector f. So the vector f has components p, q, r. The differential operator is the three differentials, partial with respect to x, partial with respect to y, partial with respect to z. If you put those into a cross product, then when you evaluate this determinant, it turns out that's how you get the curl. So it's a cross product, and so let's do an example. We have this vector field where p is this xz, q is xyz, and r is negative y squared. So let's find the curl. The curl of f is going to be, I'm going to do this using the determinant. So we have in the top row ijk. The next row we're going to have the partial with respect to x, the partial with respect to y, and the partial with respect to z. And then we're going to have xz, we'll have xyz, and then we'll have negative y squared. So remember how we evaluate this. So we're going to have, it's going to be the I times the partial of negative y squared with respect to y, which is going to be negative 2y. So what I'm doing first is I'm going to go down I'm going to take these diagonals positive, and that's going to wrap around there, and then that's going to wrap around this way. We've got plus j times the partial of xz with respect to z, so that's going to be an x, and then plus k times the partial of xyz with respect to x, that's going to be yz. Now we're going to be subtracting these going in the opposite direction. There's going to be the partial, it's going to be I times this diagonal going down. We're going to have the j, oops, this is a little bit, I don't want to cross over this stuff too much. We're going to have these, and they'll have k. So these are the parts. We're going to be subtracting each of these. I times the partial of xyz with respect to z, that's going to be xy, minus j times the partial of negative yx with respect to x. Oh, sorry, it's negative y squared with respect to x. That's just a big old 0. And minus k times the partial of xz with respect to y, that's also a 0. So this is going to be the I vector times negative 2y minus xy plus the j vector times x plus the k vector times yz. which I personally like so much more to put it in this form, negative 2y minus xy comma x comma yz. So you can see we have a vector field here. The curl is a vector field, and at any point in the vector field f, you can evaluate the curl and it will give you a vector. So what is that vector? I am going to jump to this slide just to show you at the bottom. The curl represents the axis of rotation of particles near xyz. So I guess if a particle was at the point xyz, then the curl is giving you the speed at which it's rotating. So the axis of rotation is given by the direction of the vector, and then the magnitude of the vector indicates the rotational speed. And I'm not going to get too much into exactly what that means. But if the curl is the zero vector, then that means that the vector field is irrotational at that point. There's no swirling or twirling. The particles are not rotating at that point in the vector field. Now, back up to the top. So a couple of these theorems we'll mention. We have a theorem. If you have a function of three variables, if you have continuous second order partial derivatives, then the curl is going to be the zero vector. The curl of the gradient of f is the zero vector. So if a vector field is conservative, this is really the bottom line. Well, it literally is the bottom line of this theorem. If f is a conservative, if capital F is a conservative vector field, it has zero curl. And in particular, gradient fields are conservative vector fields. So the curl of a gradient field is always zero. Now the converse isn't always true. If a vector field has zero curl, it doesn't necessarily mean that it's conservative. But if it's a vector field defined on all of R3, as long as the component functions have continuous partial derivatives, then that's enough for us to make the converse, that if the curl of f is the zero vector, that means f is conservative. So this is a great check we can use to find out if a vector field is conservative. We can just find its curl. Of course, finding the curl requires doing a cross product, so that might not be so much fun. But as long as the vector field is defined in all of R3, and if it has continuous partial derivatives, if the component functions do, then you can make this converse statement. So let's show that this is conservative, this function. Now you can see this is a vector field where the component functions are just polynomials. And so for that reason, we know that this is it's defined in all of R3, and the component functions have continuous first order partial derivatives. So if the curl is zero, then it's conservative. So let's find the curl. So it's going to be the determinant of the I vector, j vector, k vector, and then the partial with respect to x, partial with respect to y, and the partial with respect to z. And what we've got down below is y squared z to the third. We have 2xyz to the third, and we've got 3xy squared z squared. The curl then evaluates. We're going to let's do it like this. It's going to be the I vector times the partial of 3xy squared z squared with respect to y. That's going to be 6x y z squared, minus the partial in the other direction of with respect to z. That's partial of 2xy with xyz to the third with respect to z. That's going to be 6xyz squared. Oh, look at that. That's a 0. Okay, so we're plus the j vector times the partial with respect to z of, so the j vector times the partial with respect to z of yz to the third. That's going to be 3y squared z squared, minus the partial with respect to x of this here, which is going to be, of course, 3y squared z squared. Then we're going to have plus k vector times, what do we have? K times the partial with respect to x of 2x, y, z to the third. That's just going to be 2y, z to the third minus the partial with respect to y of y squared z to the third. That's going to be 2y, z to the third. This is just a big ol' 0, 0, 0. This is the 0 vector. So that, therefore, f is conservative. Let's try to find a potential function. A potential function is going to be one such that f of x, y, z needs to be the integral of y squared z to the third dx. Well, this is going to be x, y squared z to the third plus some function, I'll call it g of y and z. That could be anything, but we also know that the integral of the second component, 2x, y, z to the third dy, right, is the same thing. Now this is going to be x, y squared z to the third plus some function h of x and z. Well, so far it looks like we have it. We don't need to have any other function tacked on. But let's just make sure the last one works. I'm pretty sure it will. 2x or 3x y squared z squared dz is going to be x y squared z to the third plus some, what letter can I use? U of x and y, and we have these in common, and these can all be 0 or some the only thing they could be is some constant. So I'm going to let my f of x, y, z, the potential function, it could be any potential function. I can leave that constant term as 0. So it's just going to be x, y squared, z to the third. Bingo, we got it. Divergence is found when you take it's the sum of the partial derivatives of the components. So actually, the divergence of f the divergence of f is a scalar function. So at any point in the vector field, the divergence is a scalar. It's a number, and it's going to be given. It can be found, so using this differential, this gradient operator, you can write the divergence as the dot product of the gradient operator and the vector field. So the divergence is interpreted as, it's the net, at a point x, y, z, the divergence is the net rate of change of the mass of, like how is the mass of this fluid or gas with respect to time changing at that point per unit volume. So if the divergence is 0 at some point, that means the vector, or if the divergence is 0 everywhere, that means the vector field is incompressible. So if you had a vector field, probably like if a vector field was describing like mercury flowing around, or probably any most liquids, I don't know if there's any compressible liquids really. Well, you can compress some liquids a little bit to change their temperature, but like some incompressible liquid, yeah. If you had a vector field with like a bunch of metal ball bearings like moving around and stuff, I don't know, that's a good example. But a vector field describing some incompressible liquid flowing around stuff, well, that would be incompressible, right? The divergence is going to be 0 everywhere because there's no place where it's getting denser in some areas and less dense in others. But gases are going to not bring compressible vector fields. Okay, so let's find the divergence of this vector field. Divergence is relatively fast to find because the divergence, you just take the partial derivative of each of these components with respect to x, with y, and z. And so the divergence of f is going to be the partial with respect to x of xz plus the partial with respect to y of xyz plus the partial with respect to z of, this is a negative y squared. So what we've got here is a z, and then we'll have an xz for the second one, and then we're going to have a big old 0 for the last one because it's constant with respect to z. So this is the divergence of this vector field. You can see it's a scalar. This is not a vector. The divergence gives you a scalar. So a theorem, if you have a vector field, as long as your vector field has continuous second order partial derivatives, the divergence of the curl of the vector field will always be exactly 0. The divergence of the curl is going to be 0. Now, actually, I'm not going to be going through the proof of that here. I may do that in another video, but we can use this to show things. So, for example, we want to show that there's no vector field that has a curl this. Well, if there is some vector field where this is the curl, if f exists with the curl of f xz xyz negative y squared, then the divergence of xz xyz negative y squared equals 0. Right? Because the divergence of the curl of a vector field must equal 0. But what is the divergence? This gradient operator dotted with xz, xyz, and negative y squared. What is this? It's going to be the partial derivative of xz with respect to x, of course, that's z. We just did this a second ago, right? It's z plus xz, which is not equal to 0. We just did this. So this vector field is not the curl of any existing vector field. It's just not possible for a vector field to have this curl. Yeah, so that's not possible. The divergence of a gradient field. If we have a gradient field and we want to find out what its divergence is, it's going to be given by these like second partial derivatives. And so because a gradient field is the gradient operator times f, right? That's the gradient field. If we dot that with another gradient operator, we can use this this notation of this gradient squared. This is called a Laplace operator, and this is used all over the place in physics. But I'm not going to be able to go into much more detail at the moment because I'm not an expert on this. We're getting towards the end of this course, but there's a lot of stuff you'll find in more complicated in fluid dynamics and fluid like engineering and stuff, where you'll be using Laplace operators. But this anyway does it for the curl and divergence lesson. So we'll put this into practice, use some practice, and you'll become an expert like me. Bye.